Okay, now let's talk about the death of stars, chapter 23. Okay, so we'll talk about what happens when a star like the sun ends its life. We'll talk about what happens when a star that's bigger than the sun ends its life. And that results in something called a supernova or a neutron star, or you could even get a black hole. And then we'll talk about how there are some special cases where a low-mass star can end up as a supernova if they have a stellar companion, and then this thing called a GRB, or a gamma ray burst. Okay, so what happens is basically a star, like the sun, as it burns, it's filling up its core with helium. And then as it continues to burn, it can end up putting a carbon core in there. And then once it runs out of this and gets hot enough to fuse the helium into carbon and some oxygen, once that helium is out, this final collapse here is the last thing. And it can't collapse even further to get carbon and oxygen to fuse. So you start out with a star like the sun, and then it's fusing hydrogen into helium in the core, and after a little while it will start fusing the helium into carbon, and then after a little while you'll just have this carbon core, and the carbon doesn't fuse anymore. It doesn't have enough gravity to do that. And remember, in between each of these stages, after you run out of hydrogen, the star collapses down until it can start fusing helium, and then it starts fusing helium, and then when it runs out of helium, it collapses down again. But there's not enough pressure when you have a low mass star to begin fusing carbon into something. So the star just collapses down and shrinks until it is a very dense object, and it's something we call a white dwarf. Okay, which happened to be my nickname in college. Okay, so the core continues to shrink until it reaches a density nearly 1,000,000 times the density of water. So if you take water from your sink and compress it down, so take a cup of water and make it 1,000,000 times smaller, that's how dense a white dwarf is. Now, this is really crazy because stars, when you have enough matter like that to compress all of that down into a small area and to create that density, think about what's happening. You're taking an electron, you're taking a proton, you're taking a neutron, let's say, and you're really removing the space between them. So the electrons get really trapped in there among all the other elements. And then you get another electron right next door and another electron. And so now what happens is you have something called degeneracy. And degeneracy is when the electrons get compressed into the same area. They cannot occupy the same area, so they just build up and create a minimum size. And so that's basically what's happening. Wow, excuse me, that's embarrassing. Okay, you can only shrink so far before the electrons resist being pushed closer and closer together. This is something known as the Pauli exclusion principle, and that prevents electrons, or it describes the phenomena of electrons refusing to be any closer to each other. So there is what we call a degeneracy pressure. So now think about what's happening in a star. You always have gravity pushing in and some other force pushing out. Normally it's fusion pushing out, but when you run out of fusion as a source, what keeps the star from collapsing into a black hole? In the case of a white dwarf, in the case of a star like the sun, its final state, its size that it ends up shrinking down to and stopping, is limited by the electron degeneracy pressure. That is the pressure preventing gravity from fully collapsing the star down. So that's called electron degeneracy. And that is the reason that a star does not fully collapse, and why when the sun dies, it will become a white dwarf and not a supernova and not a black hole or some other thing. So the electrons are trapped in there in something called electron degeneracy, and that's what prevents the star from collapsing all the way down once its fuel source runs out. So again, you have a hydrogen star fusing into helium, and then helium fusing into carbon, and then carbon, there's not enough pressure to actually fuse carbon, so once you exhaust the helium in the core, you just have a carbon star left over, and then you end up with what we call, this carbon star is called a white dwarf. Okay, and there's something called the Chandrasekhar limit, and the Chandrasekhar limit is the limit of the mass of a star that ends as a white dwarf. And so let's see, what are we trying to say here? Yeah, so the Chandrasekhar limit is if it's above 1.4 times the mass of the sun, that's when you have a supernova. So the Chandrasekhar limit is the limit for a size of the sun. So if this is a star and this is a star, and let's say that's the sun, and this star is 1.4 times bigger than the sun, this star will end up as a supernova and will explode. This star will not end up as a supernova and it will not explode. So the sun will end up as a white dwarf, and that's it. Nothing bad will happen beyond that. And this is just a plot of the size of a star and its mass. And you can see that there's a non-linear, it's more of a little curved thing here. That's just showing you that as the mass of a star increases, the radius gets smaller and smaller, which makes sense because gravity gets bigger and bigger and bigger. So this Chandrasekhar guy is pretty amazing dude. We can read about him there. Okay, so here's your main sequence, right? A star like the sun, 1 and about 5,000 there. The sun, it will move up, it will do a little jog here, it'll end up as a red giant, and then sweep around until it ends up in the lower left corner as or sort of the bottom left half, as a white dwarf on the HR diagram. So this is an HR diagram, brightness versus temperature of a star, and it's showing you as it evolves how its brightness and temperature changes. Basically, it stays the same brightness and gets hotter and hotter and hotter and hotter, and then starts getting cooler and cooler and dimmer and dimmer and dimmer as it comes back around, which is pretty cool. Okay, so this is a cool picture of one of the brightest stars in the sky, Sirius. And if you look really closely at Sirius, Sirius has a white dwarf companion. We've talked about this before. Now, there's an interesting thing here, like the sun, it will emit mass as it ages, as it evolves, and that ends up as a planetary nebula. So keep an eye on that. Okay, so low mass stars, what do? For sure, they end up as a white dwarf. Okay, so a low mass star like the sun will end up as a low mass star. So it turns out that if you're about 8 times the mass of the sun, after it shrinks down and loses some of its mass in a planetary nebula, that 8 solar masses translates to about 1.4 masses for the white dwarf mass. So the star will start out as this size, and then as it ages, a lot of mass gets lost, and then what's left over is 1.4. As long as it's less than 1.4 times the mass of the sun, it will not explode, it will be a white dwarf. So to start out, we generally divide a high mass star from a low mass star. A high mass star will be greater than 8 times the mass of the sun. A low mass star will be less than the mass of the sun. So something like the sun, it says it'll lose about 45% of its mass. So the sun will definitely have a mass less than 1.4 times the mass of the sun. All right, but if you have more than 8 times the mass of the sun when you form, you have a different fate, because you can fuse carbon And so after you run out of hydrogen, you fuse helium. After you run out of helium, you fuse carbon. After you run out of carbon, you fuse neon. After you run out of neon, you fuse oxygen. After you run out of oxygen, you fuse silicon and sulfur. After you run out of that, you start to fuse iron. And when iron starts to fuse, instead of releasing energy, it takes energy. So instead of the two forces out, fusion out, and gravity in, you have two forces in. You have gravity in, and fusion energy is taking energy out of the star, and it collapses. And when that happens, instead of electron degeneracy, instead of a white dwarf where the electrons are trapped together, the electrons and the protons combine and form neutrons. And so then in a normal gas, you'll have electrons, protons, and neutrons, and the electron will be flying around like crazy. In a white dwarf, the electrons are all trapped on top of each other next to the protons and the neutrons, and this pressure is what keeps the star from collapsing even further. Well, in a high mass star, the pressure is so strong that the electrons and the protons combine and they form a neutron when that happens, and so you end up with a star made 100% out of neutrons, and that's called a neutron star. So if the star is 8 times greater than the mass of the sun, it's going to end up as a neutron star. Collapse all the way down. It'll go supernova, and what's left over is a neutron star. Okay, so here's some pictures of, befores and afters. And let's see. So the bottom is before, so you can see, boom, there's that supernova. Where is it down here? It's gone. You can see, wow, there's no supernova here, boom. No supernova there, and then boom. And then same thing, no supernova here, and then phew, huge light. No supernova, and then boom, big supernova, goes crazy. Okay, and then, so what happens to a star at the end of its life? As long as it's 8 times the mass of the sun or less, you'll get a white dwarf left over. If it's 8 to 10 times the mass of the sun, you'll get a different flavor white dwarf. If it's 10 to 40 times the mass of the sun, then you get a supernova explosion that leaves behind a neutron star. And if it's greater than 40 times the mass of the sun, you collapse the neutrons even further down, and they disappear into the event horizon of a black hole, and it collapses fully and erases a corner of the universe. Okay, so these are really beautiful images of what we call supernova remnants, and supernova remnants are these just wonderful results of the stars exploding. Just showing you all the gas and dust that they emit out into space. And they're the same picture, composite image here. You've got the X-rays and Hubble, the visible light. Look at the visible light, you can barely see anything. And then infrared, and you combine it all together, and you get this really wonderful image. So those are called supernova remnants, and they allow us to study the results. And they last forever, so we can see what's going on over time and where these remnants are. So supernova remnants, in 1987, there was a really nice supernova that went off. We've been watching ever since. This is a supernova from the year 1006, or actually I think it was 1054, something like that. Actually, no. So yeah, 1054, this is the supernova that was recorded in 1054, and then 1006 was a different one. But this is the supernova remnant of that one from the year 1006. And look at this beautiful flat edge up here where the supernova remnant is running into the edge of space, the interstellar medium. We can actually learn about the interstellar medium there and see that this is nice and round like a normal explosion would be, and then this flat edge means that the interstellar medium there is a little bit different density than the area around it, and that's what's causing that. There's another one. This was in 2014, M82. It was so bright. You could see this with even a very basic telescope. We took a bunch of pictures of it. That's a really cool picture there. Supernova 1987A. And there it is, the ring. Okay, so so the star that exploded in supernova 1987A, the fusion, you go from hydrogen to helium to carbon to neon to oxygen to silicon, and then the core collapses when it gets to iron. Now, it lasted 8 million years in hydrogen fusion, so that's not a very long time, and then 1 million years in helium fusion, and then carbon fusion only lasted 2,000 years. Neon fusion only lasted 6 months. Oxygen fusion lasted a year. Silicon fusion lasts only a day or so before it runs out of all its fusion. And then the core collapses in less than a second, and then it explodes. And so this is really cool. You can see the brightness of a supernova over time, and we can measure that with all of the supernovas to understand what's going on. The important thing is that the heavy elements on the periodic table of the elements, gold, platinum, silver, uranium, iron, all these things, especially iron, right, come from supernovas exploding, or neutron stars emerging, or really catastrophic events. So most of the stuff we see in the universe is hydrogen or helium gases like that. Where do these heavy elements come from, like uranium and other things? They come from supernova and other stars colliding. Now, what's cool is that the neutrinos, we've talked about this before, the neutrinos that are generated in the nuclear fusion shoot right out and they don't interact with anything. The light has to bounce around before it escapes. So we actually detected the neutrinos coming from 1987A before we saw the visible light of the explosion, which is kind of crazy. So this is pretty cool to read about to understand that. Okay, so neutron stars, like I said, if you have a high mass star and when it dies, after it goes supernova, it leaves behind what's called a neutron star. And we'll talk about the black holes later, but most of the high mass stars will end up as a neutron star. Okay, and so a neutron star, this is a really wonderful image. This is the Crab Nebula, and there's a neutron star at the middle here, and you can see these wonderful jets of energy, happy little jets, shooting out from both directions, and then we've got this swirl of energy swirling around, and I don't know if there's another picture of the Crab Nebula here, but basically what's happening is the discovery of the neutron star is the fact that the neutron star, if the star is rotating like that, it ends up, because of its magnetic field, accelerating particles in these two opposite directions. And then as the star rotates, it's like a lighthouse, as it rotates around. So the periods of a neutron star can be pretty fast, like milliseconds, like really, really fast. It's just spinning around really fast. There's one there. I'm looking for some light curves. They don't have any light curves of a neutron star. So let's find one. Okay, light curve, neutron star. All right, images. Okay, blah, blah, blah. So there's some there. And let's see if we can find a... what's this one? Yeah, so there's some light curves there showing you the brightness over time. Let's see. Let's go to period neutron star. And well, they don't have really good. It's a pretty technical thing, I guess. But they're like milliseconds, so those light curves are super fast. Okay, so basically, if you look at the frequency of a neutron star, you'll see it's light, and they can blink really fast. So that's why they call them pulsars, because they were like lighthouses, where as they rotated, you get these really bright signals coming at us. And for a second, we figured it was aliens, but it turns out it was neutron stars. Okay, or pulsars. So pulsars were discovered first, and then we realized that pulsars, which it's just this light that's boom, 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 we realized it was a neutron star that must have been doing it. Okay, so that's what a neutron star is. Now the evolution of binary systems. So binary systems are when you have two stars orbiting each other. So let's say you've got two stars. Here's your primary star and your secondary star. Now what happens? The primary star might be a little more massive, so it's going to evolve quicker. So it goes into a red giant, and then it ends up with a white dwarf. The other star, since it's lower mass, lives a little bit longer on the main sequence. So now you've got a white dwarf and another star here, just like Sirius. Well, when this star dies, it'll swell up into a red giant. And at that point, you see this? There's mass from the red giant adding to the white dwarf. Now, we talked about the Chandrasekhar limit. As long as it doesn't exceed it, it won't go supernova. Well, if this red giant starts putting on enough mass from gravity, accreted onto the white dwarf until it reaches 1.4, at that point, boom, smithereens. The star will explode, and it explodes at about the same spot every time. And that's what makes it a standard candle, which means it has a known brightness, but that's also called what's known as a type 1A supernova. Okay, the type 2 are from high mass stars when they die. Type 1 is from a low mass star, only in a mass transfer binary. So this is a binary star system, and we call it mass transfer because the red giant will deposit its gas onto, or its material onto the small, it'll transfer some of its mass to the little guy. Okay, so that's what a type 1A supernova means. And that's from the star going above the Chandrasekhar limit. Okay, so millisecond pulsars, these are very fast pulsars. They rotate, 500 times a second or something, extremely fast. And we can see them by, again, looking at their light curves. So gamma ray bursts are these really insane amounts of energy that were coming from space. And we couldn't understand what it was for a long time. And the first measurements were, let's see if it mentions it here, the first measurements of gamma ray bursts were from secret, let's see, I don't know if they mentioned it, but they're talking about Lawrence Livermore. Anyway, in Los Alamos, I guess they don't mention it. So, anyway, looking for nuclear weapons launches, they were detecting gamma rays from space, and they didn't know if they were nuclear weapons or something else, but it was a classified mission, so they couldn't announce the discovery of the gamma ray bursts until they got clearance for it. Yeah, here you go, Vela satellites in the 1960s. And so it took a while before they declassified their discovery and let people know about it. Okay, blah, blah, blah. So, yeah, there's your host galaxy, and then there's the source of the energy coming from these gamma ray bursts. So gamma ray bursts, they're extremely bright signals from space, and we didn't know what they were for a long time. And yeah, there's a really nice one here by Swift. X-rays on the left, visible light on the right. So look at the difference there. Okay, so so there's, yeah, let's see what they're talking about here. Yeah, so there's two types of gamma ray bursts here. We're talking about short duration gamma bursts, or ones that are longer duration. And so the longer duration ones are from stars that are going supernova. The shorter duration ones are for stars as they collide together. And when they collide, they emit these huge amounts of energy. Okay, so we'll talk about this when we talk about neutron stars merging, or a neutron star and a black hole, or when black holes merge. We'll talk about that later when we talk about black holes and LIGO and the curvature of space-time and that kind of stuff. Okay, so gamma ray bursts, since they're so bright and they come from across the universe, it allows us to understand how old the universe is by looking at how redshifted the light is and all that other good stuff. Okay, so in summary, low mass stars end up as a white dwarf, and a low mass star is a star with 8 times the mass of the sun or less, and when it dies, it's going to leave behind a white dwarf that is of size 1.4 times the mass of the sun or less, which is the Chandrasekhar limit. The reason the white dwarf is the size it is no longer because of fusion pressure, but because of electron degeneracy pressure, and that keeps the white dwarf from collapsing even further. High mass stars overcome the power of the electron degeneracy pressure, and they leave behind a neutron star or a black hole, depending on how massive they are. The difference between a low mass star and a high mass star is it can continue fusion beyond carbon and continue fusing all the way to iron. And what then happens, the iron collapse causes a collapse because of it's using fusion energy to fuse. It's using energy from the sun to fuse rather than releasing it during fusion. And that results in a type 2 supernova. Type 1a supernova is when a low mass star and a white dwarf evolve together, and the low mass star, when it turns into a red giant, deposits its material until it goes above the Chandrasekhar limit, and then it will go supernova with the same brightness every time. Pew! Pew, pew, pew. And so those become standard candles, and those are ways for us to gauge distances across the universe. And then gamma ray bursts were discovered by the Department of Defense in the 60s. CIA discovered it, and then I think it was the CIA, could have been DOD, I don't know. And it was declassified shortly thereafter, and they turned out to be these very high energy signals coming from space. And there's short duration and long duration, and those two types come from different sources. Okay, talk to you guys later.